Hi, so in this video we are going to go over the S parameter results of the simple 50 ohm single-ended transmission line, which is a coplanar waveguide, or rather a grounded coplanar waveguide. We are interested to see what kind of insertion losses and reflection parameters we get with the GPPC connectors attached and with these SMPM cables. Please note that we do not have a calibration kit for the SMPM connectors, so there is no way for us to de-embed the effect of the SMPM cables. So whatever insertion losses and S11 which you're going to get are including the effects of the cables. And we have done an estimate, we have come up with an estimate of the insertion loss of the entire circuit from port 1 to port 2 of the VNA, and I'm going to show that block diagram right now on the screen, so you can get the estimated losses of the cable, which is 3 dB, and the estimated loss of the GPPC connectors would be 0.25 dB, and you can see the loss parameters of the PCB trace, the transmission line. So the entire S21, or the insertion loss which we have estimated, which is our expectation, is around minus 9.27 dB. And yeah, shortly I'm going to show you what kind of actual results which we are getting. um, yeah, so by the way, the cables which we are using are the same from the last video which I recorded. So these are okay, let me focus. Yeah, SCA 92086, and 36 is the length of the cable in inches, so it's a 36-inch cable. According to its data sheet, per foot we can expect a loss of 1 dB at 10 gigahertz. So 36 inches means 3 feet, and we are going to expect a loss of 3 dB per cable. So for two of these cables, it would be a 6 dB loss. All right, so let me bring my camera down and I'll show you what kind of results which we are getting on the VNA. We are getting a port-to-port loss of 10 dB. As you can see, I've put the marker on 10 gigahertz, and on the top right corner of the screen, you can see a loss of 10 dB at 10 gigahertz. And that is including the cables, the SMPM connectors, the GPPC connectors, and the transmission line on the PCB. Uh, as per our estimate and the simulation, I'll put up the block diagram right now. We are losing 6 dB on the cables, and then at the connectors we are losing 0.5 dB, and the rest of the loss is due to the PCB trace. That is my assumption, but there is another connector which I have not taken into account, which is the SMPM connector and the K-type connector on the cable. So it could also be that the cable is contributing more than 6 dB of loss. So that we can only find out once we have um, an SMPM calibration kit or any way to de-embed the cables. Even a SMPM through connection would work, but we are yet to purchase those, and we are yet to calibrate and de-embed the SMPM cables. So there's a little gray area in the measurements, why we are as to why we are getting a difference of 0.7 dB between the practical and theory. But I also think that when we are operating at 10 dB of loss, or the power levels of minus 10 dB, a margin of 0.7 dB is not very high. Um, and at the same time, we have to consider that the laminate which we are using, FR370HR, that is not the perfect choice for experiments at 10 gigahertz or above. So yeah, in conclusion, I would say that the test is successful, and we are getting results which are very close to the expected results. There are a few unknowns which we are yet to solve, like the losses, the actual losses of the cables. Maybe try and de-embed the cables in the measurements. I think that's it for the S21 parameters. Let's have a look at the S11, and then we can finish the video. Yeah, so S11 in my opinion is even better than the S21 parameters in terms of its performance. Let's say we are accepting um, a level of minus 20 dB for the reflection, then we can go up to 15 gigahertz. And if we accept around minus 15 dB, then we can go up to around 20 gigahertz, I think. Yeah, so in terms of reflections, it's quite good. The matching and everything is, I would say, very much acceptable on the PCB. But at the same time, anything above 10 gigahertz is not right now our frequency of interest. So yeah, we can see any frequencies around 10 gigahertz or below 10 gigahertz is under minus 20 dB of reflection. So that is pretty good. All right, so that was it for the S parameter testing of the simple 50 ohm single-ended transmission line. In the next video, I will try to give you the S parameter testing of the bias T. Let me see, just increase the brightness. Yeah. So we have also prepared a bias T, although it is not very optimized. But yeah, I'll cover this in the next video. That's about it for this video. Thank you for sticking around till the end, and I will see you in the next one. Goodbye.